All right, we have here a system of nonlinear differential equations. You can see it's nonlinear because of the multiplication between dependent variables. There's an x term here, there's x squared and xy terms here if we FOIL all this together. So it's nonlinear. We want to find the equilibrium solutions. To find the equilibrium solutions, we just set the derivatives to 0. Equilibrium happens when there's no change. So there's no change when both x prime and y prime are simultaneously equal to 0. So we set them both to 0, right? Now, I want to look and think which of these is easier to deal with. I think the second one is my starting place because it looks like the easier equation to deal with. So from the second equation, if this is to equal 0, I know that either x equals 0 or y equals -2. There's a couple of ways that that can be 0, and those are either x has to be 0 or y has to equal -2. So I'm going to take those one at a time. Let's take x equals 0 as a case and plug that back into the first equation. So we plug that back into the first equation, and the first equation looks like a -0 minus y times 1 minus 0 minus y. And we want that to be 0. So that looks like y times 1 minus y equals 0. And that means either y equals 0 or y equals 1. So those are the possibilities. If x is going to be 0, if the second equation is 0 because x is 0, then the first equation, in order to be 0, has to have y equals 0 or y equals 1. We get a couple of options here, a couple of points. We get the point x equals 0, y equals 0, or the solution x equals 0, y equals 0, and we get the solution x equals 0, y equals 1. Those are both equilibrium solutions to this nonlinear system. We're not done because we didn't track through the second case. The other case from this equation was that y equals -2. So if y equals -2, same procedure. We're going to take that, we're going to plug it into the top equation here. That gives us a negative x minus a -2 is going to be x plus 2 times 1 minus x minus a -2, so that's a plus 2, equals 0. And let's see, that means I have either x equals -2 from this term, or x equals +3 from this term. And so the equilibrium solutions are x equals -2. This was for y equals -2, -2, or x equals 3 with y equals -2. In the end, we have 1, 2, 3, 4 equilibrium solutions to this nonlinear system of differential equations. What does it mean to be an equilibrium solution, right? If I start with initial conditions x of 0, y of 0, if I start at the point 3, -2, one of my equilibrium solutions, right? If I start at one of those equilibrium solutions, then I know that x prime is 0 and y prime is 0, so there's no change in x, there's no change in y. That means I just stay at that equilibrium solution for all time. We start there. If it's an equilibrium, it can't change because the derivatives are 0, so we stay there. That's what it means to be an equilibrium solution. There are 4 places for this particular nonlinear system of differential equations. There are 4 places where that can happen. There are 4 of these equilibrium solutions. That's how we do it. Often try to pick the easier function to deal with, find where that is equal to 0, and then plug that into the other one. There's often lots of little cases to track through, like we had here. If x is 0, what happens? If y is -2, what happens? Track through it all and get the complete list of equilibrium solutions. We won't know in advance how many there are because it's nonlinear. We aren't going to know if there's 2 or 4 or 8. We just have to track through all of the different cases. That's it.